Alright, so in the last video, we covered how to detect heteroskedasticity. In this first video of multivariate regression, of the multivariate regression series, I'm going to go over how to actually detect this heteroskedasticity. So we went over how we detect it, and in this video, I'm going to go over how we can correct it. And so, not only this video, but for the coming future, a lot of these notes, I'm not really going to provide specific examples. One, because they're difficult, but also because most of these methods are done by software. And when I learned through these concepts in class, I didn't really have to, we didn't really have to solve these problems through like algebraic methods. So I'm kind of just going to do the same. Once I'm done with all of these videos and pretty much done with the series, I'm gonna kind of like make a recap video on both the linear regression and this new series of multivariate regression, which covers like a lot of these methods done in software. So I'll make it for that, but most of these videos from now and later are gonna be on just concepts, even with all the algebra shown here. Alright, so one method of detecting correcting for heteroskedasticity is called the wide robust standard errors. So given this variance function here, we assume that this is kind of our unknown residuals, because if it has heteroskedasticity, then we don't know, our residuals are inconsistent. And so we're in the second part of this equation, we're calling this the unknown form of the error. And then we're also providing the degrees of freedom right here by dividing by n minus 2. And so what this test does is it will correct for heteroskedasticity, but it won't, it will only adjust the standard error and not necessarily the form of heteroskedasticity. And in consequence, by doing so, this no longer becomes our best linear unbiased estimator. And so what I mean by the wide robust standard errors not correcting the form of heteroskedasticity is we don't know the ideal regression like functional form, if it's linear or if it's quadratic or whatnot, and that's why it's no longer blue, because the function must be linear for it to be our best linear unbiased estimator. And that results transitions to our second method called the weighted least squares. Now, just like the name suggests, the weighted least squares not only corrects for the form of, or not only corrects for heteroskedasticity, but it also corrects for the form of it, and therefore makes it our best linear unbiased estimator. So our weighted least squares, like the name suggests, it'll weight the variables that are more meaningful or closer to the actual fitted function, and that's why we minimize the squared errors. If you can see up here, we'll call this just the plain variance square or standard deviation squared, the variance. This is we're assuming this is kind of like our constant known variance. And then the h of x, called the skedastic function, is the part of the error where we don't really know, the part that makes it heteroskedastic. And so what we can do algebraically is, if we divide all the variables in the regression by the square root of the skedastic function, then we actually have our error, like right here. We have our errors our variance times the stochastic function divided by the stochastic function, because we're dividing it here also. And now we have our known variance, or our constant variance, that makes our variance homoscedastic. Now, if you're asking why we divided by the square root and we didn't do it here, that's actually a good question. I'm pretty sure I didn't make an error mistake in writing this, but nevertheless, the general concept is the same. We're dividing all the variables by the stochastic function or the unknown variance function, and that allows us to obtain the known variance function. All right, moving on, we have our third method of correcting for heteroskedasticity called the GLS. And this is when we have a known variance form. The generalized least squared, it involves a general like 4-step process generally. That's what I made into. It's not like a formal 4-step process, but we extract the residuals from the function, which is the first step. And then we'll regress the error squared, the logged form. And because we log it, we have to unlog it. And so our right side of the equation, we have to exp every equation, exponent every equation. And then this is how we obtain the stochastic function. The intercept is not part of the stochastic function because it's not included in the error. And finally, we can transform the data by, again, dividing by the stochastic function. This might be a little confusing considering that it looks pretty similar to the WLS, except we're kind of going backwards. And so this is pretty similar to the WLS, but this is when we know our variance function. Actually, this is also when we know our variance function. This is okay. This is when we don't know our variance. This is when we know, and this is also when we know. So they're just slightly different methods, but both of them assumes that we know the variance function. And lastly, if our x variables are comprised of dummy variables or binary variables, we take a similar approach to the previous couple methods. We'll get the stochastic function, stochastic function, or the unknown errors part of the function. We'll power it by E, and then we'll find the FGLS estimate. So the process is the same. Algebraically, it's probably different, but dummy variables are, at the end of the day, another type of variable. So this video didn't have any examples. Neither was it algebraically explicit, but it's more of an overview of the different types of corrections we can do to correct for heteroskedasticity. Remember that heteroskedasticity, when we have it, our model is our model in our data set. It's considered unbiased, so we could still use our coefficients. Sorry, not our data, but our model is unbiased, so we can still use our coefficients in our regression function. They're still made meaningful, but our standard errors are correct. So stuff like hypothesis testing or in confidence intervals, we can't do anything like that. But with the utilization of these 4 methods, we actually can. And that's why, or we can use the hypothesis test and create confidence intervals, which is why this part of heteroskedasticity is very important. All right, that's pretty much it for heteroskedasticity. In the next video, I am going to give an outline on in time series models. Time series models, so basically which are data that include time. They will still include a regression function, just a different variant.